Welcome to the first lecture of Digging into Data. Today what I'm going to talk about are what are the major ideas of the course. I'll then talk a little bit about how the course is organized, then introduce some of the technological tools that we'll be using. So first, what can we do with data? Data are everywhere. When you watch a movie on Netflix, that generates data. When you buy products on Amazon, that generates data. The hundreds of articles of science that sit on the shelves of a library also constitute data. The genetic code in your body also constitutes data. The thoughts in your head that arise from neurochemical reactions in your brain also constitute data. Even when you're goofing off in class, participating on social networks like Facebook, Twitter, and Google+, that also generates data. Data are very important to our world. The prices that we pay are determined by markets, and the prices that those markets use are the product of many different market participants using data to agree on the price of commodities, of equities, and many other products and services. We can use these data to solve problems. For example, if you look at Netflix, we can ask the question, will a particular user like a particular movie? And given their history, we can determine what about the movies they liked or didn't like are like the movie that we're trying to make a guess about. One of the things we'll talk about in this class is how to break down a data set to help us answer this problem. Given a bunch of data, we'll divide it into training data, testing data, so that we can learn a model from training data, apply it to testing data in a systematic way, so that we'll be as confident as possible that we'll be able to predict well on new data that we haven't seen before. We can also do data to help people understand the large amounts of information that they're confronted with on a daily basis. For example, if you have all of the images on someone's hard drive, you can group those images into clusters so that people can more easily find the kinds of images or specific images that they're interested in. Sometimes data even are a life or death issue. For example, if you have the genetic information of an individual, you can predict whether they will likely suffer from a disease even before they start showing symptoms. And if you're interested in making a lot of money, you can also use data to do that. There are many firms whose sole purpose is to better use the information from the web and social media and weather satellites to more accurately predict the price of stocks. At the same time, government regulators are also using these data-driven techniques to discover when people are using data in an illegitimate way. For example, to do insider trading. Data have also become very important in our electoral and political system. One of the lessons that we learned from the 2012 election is that the Obama campaign did a much better job of using data. The Obama campaign did a much better job of getting the right message to the right people. They used very sophisticated techniques to determine what were the most salient issues to particular voters, allowing them to send exactly the right message to that person to cause them to either change their view on the candidate or to go out and vote. Data-driven techniques are a part of all of our. For example, every email you read has been electronically vetted by an algorithm to determine whether it is spam or not. An algorithm can look at this message and determine what features cause this more likely to be spam. For example, it might come from a contact you don't recognize, from a country that you normally don't communicate with people from. It might be addressed to many different people, and it might use words like charity that are highly correlated with spam. This allows your email client to hide these messages from you and only show you the messages that you care about. For example, messages from people you know about subjects you care about. One of the most interesting things about this course is that the mathematical foundations for that technique, classifying an email message as spam or not, is very similar to the problem of detecting whether a particular square in an image is a face or not. And this is very beautiful, that the same methodologies that allow us to figure out whether something is spam or not can also be applied to detecting faces in an image. We extract features, we throw it into the same algorithm, and we can do very different things using the same toolset. The bottom line is data contain patterns that can help us solve problems, and this course will teach you how to do that. And we'll draw on insights and techniques from statistics and machine learning and apply them to many different fields, including natural science, web technology, finance, and policy, and whatever you're interested in. The goal of this course is to instill a fluency in how you think about modern data analysis problems, to allow you to address a problem, to address a data set, and figure out what insights you can extract from those data, and also understand when that isn't possible or when it's very difficult, and how to communicate that to decision makers and lay people. One common theme that we'll see again and again in this course is a pattern of first getting data, putting it in a form that we can use, using a learning algorithm to extract some insight from those data, and applying that to some new piece of data. For example, taking all of a user's history on Netflix, taking a new movie that they haven't seen before. For example, how many stars would this user give to this movie? There's no one way to organize a course on this topic. So what I've tried to do is I've tried to build a course about a family of techniques that all use the same foundation. That foundation is the language of probability. After I've introduced that foundation, we'll then talk about both supervised and unsupervised methods for different kinds of data, discrete data and continuous data. We'll also talk about some of the engineering decisions that you'll have to make, how to prepare data, how to represent features, how to evaluate models, and understanding when things go wrong and how they can go wrong. So let me dig down a little bit deeper into some of the terms that I used here: supervised learning, unsupervised learning, and then discrete versus continuous data. Supervised learning is when you have fully observed data and then you try to predict something about partially observed data. So for example, you might have emails that also have labels that say whether it is spam or not spam. On your training data, you have both the label and the original text. Then, at test time, you only get the original email text, and then the job of the algorithm is to provide the missing label. Unsupervised methods are a little trickier. With unsupervised methods, what you're trying to do is trying to get your algorithm to discover the hidden structure in data that is never really observed. So for example, you might have a museum that has thousands of images, and you want to group those images into 15 groups so that each group of images has similar content. This is a little bit trickier to evaluate, because if you gave the same task to 5 different people, you'd get 5 different answers. Nevertheless, these techniques are widely used to help people make sense of very large data sets when they don't have time to examine each individual piece of information on their own. Both supervised and unsupervised techniques can be applied to many different kinds of data. One primary distinction that we'll make about the kinds of data that we'll be analyzing is whether the data are discrete or continuous. Discrete data take on a finite set of values. So for example, if you have a car, its color can be red, green, or blue. In contrast, continuous data can take on a value from an infinite number of possibilities. For example, the weight of an elephant, the price of a car. One quick rule of thumb for determining whether data are continuous or discrete is asking, does it make sense to take the average of a value? So for example, if you have 5 elephants, it makes sense to ask, what is the average weight of the elephants? But if you have 5 cars, it's harder to ask, what is the average color of those 5 cars? Or, if you have a book, what's the average word in that book? When we combine different kinds of data with either supervised or unsupervised techniques, we get different kinds of algorithms. And because of the history of the field, those algorithms have acquired different names. For example, when you use supervised learning on discrete data, that's called classification. Supervised techniques on continuous data are called regression. Unsupervised techniques on discrete data are called clustering, and unsupervised techniques on continuous data are called dimensionality reduction. We'll be talking about each of these. Just as a disclaimer, I should say up front that I mostly work on discrete data because I work on language, an example of discrete data. And in terms of the methodologies that I use, I mostly work on combinations of both unsupervised and supervised techniques. But no matter what kind of technique that you're using, one of the primary challenges is how to represent your data in a way that these algorithms can make sense of it. So how do you take an image, a document, or a social network and represent it in a numerical way so that algorithms can understand the data and learn patterns that you can use for applications? We'll also talk about the assumptions that these models make about the data, when the assumptions are appropriate, and how to explain the assumptions to a decision maker. Now that I've introduced what the course is about, I'd like to change gears and talk about how we're going to run the class. There are 2 broad kinds of skills that you need to do well in this class: technological skills and mathematical skills. In terms of technology, we're going to be using some sophisticated programs, both R and Rattle, that I'll talk more about in a little bit. In terms of computer skills, you don't need to learn how to program, but it would help. That being said, we will use concepts that come from programming languages. You do need to know how to assign objects to variables. You need to know how to use functions, both how to call them, how to pass parameters into them, and how to accept data from them that they return. We'll also be using the command line. Now, you don't need to know all of these things right now. We'll review them, but you will need to catch up fairly quickly. In terms of the mathematics background, this isn't a machine learning course, so we won't ask you to prove anything or to do integrals, but you do need to be comfortable with the notation that we're going to be using from standard algebra. So you need to be comfortable with sums and algebraic variables. We'll ask you to take logarithms, to add, divide things, and to solve basic algebraic equations. Last year, some people had stronger foundations in some areas than others. And because we're all working together on this, I'm going to ask you for your patience if you've seen some of this stuff before. And if it is old hat to you, please help out your classmates so that they can catch up. Because it could be that while you have a very strong math foundation, you might need help on the technology side. And if this class is anything like last year's, we'll have a very diverse set of skills and you'll be able to help each other to succeed. Even though we had a very diverse class last year, just about everyone managed to get through and do some really impressive projects. Last year I ran the course as a traditional lecture-based course. Students found that they didn't have enough time for hands-on practice and to ask very specific nitty-gritty questions during class. In response, this year I'm trying an experiment. I'm going to do a flipped classroom where I'll record the lectures ahead of time, like this. And then your responsibility is to watch the video, come to class, and ask questions about it. After you ask those questions, we'll then work through clear and specific examples so that you can build confidence with these techniques so you can apply it to your homeworks and to the lectures. Because it's so important for you to ask questions, I am going to call on people randomly at the beginning of each class, so make sure that you come prepared to class with questions. This will be a part of your participation grade. The primary means of communication that I'll use in this course is the course webpage. On the course webpage, you'll see the lectures, the homeworks, and the readings. Speaking of homeworks, we'll have 4 homeworks in total, only 3 of which will be graded. For those homeworks, there are 5 late days that you can use, no questions asked, distributed over the 3 homeworks. So you can use all 5 late days on one homework, or you can divide it up using 2 on the first, 2 on the second, 1 on the last, or you can not use any late days at all. It's entirely up to you. There will also be a midterm, which will be about 2/3 of the way through the course, and a project at the very end of the course. There's more information about all of these on the syllabus, which is linked to from the course webpage. If you have special needs in terms of religious observances or in terms of test-taking accommodations, let me know at the end of our first class time. The book that we're going to be using is Graham Williams' Data Mining with Rattle and R. I think this is a pretty good book. It's fairly recent, and it does a good job of giving very specific examples. I encourage you to do the assigned reading before watching the video. This is because the readings are broader than the videos, and the videos will drill down into specific areas that I think are more important. We'll be using Piazza to manage course-related communication. I'm going to try my best to answer all questions asked on Piazza within a day, hopefully sooner. One of the main reasons that I'm using Piazza rather than Elms is because I think Piazza does a good job of making sure that students actually talk to each other and help answer each other's questions. So I really encourage you to take it upon yourselves to help your fellow students out and answer their questions if you see them on Piazza. This will be another way that you can earn participation credit. Please use Piazza not just for technical questions, but also for administrative questions about the concepts of the homework, whether you should use a particular technique on a homework, because if you have this question, it's likely that your fellow classmates do too. And one of the nice things about Piazza is that you can ask questions anonymously. When you ask for help, though, make sure that you give enough information so that I or your fellow classmates can help you out. This requires you to explain what you're trying to do so we know where you're coming from. Give a minimal example of the problem that you're having. So what's a minimal example, you ask? Well, it should be the simplest possible thing that you can do that still produces the error that you're seeing. And it shouldn't require any external data that only you have. I should be able to sit down at my computer and get the same result that you're getting so that I can help you with your problem. Now, after giving this minimal example, you should explain what you think should happen and what happened instead. Copying and pasting or taking a screenshot if you can. Because sometimes things are working as they should, and it's just a problem of matching your expectations to the underlying technology. But sometimes that isn't obvious unless you've explained both what you expect and what you get instead. Also explain what else you've tried so that I know your thought process and maybe there's an easier solution that I can provide instead. On Monday, we'll go around the entire classroom and you'll introduce yourselves to each other so that I can learn what you want out of this class and hopefully tailor the class to meet your needs and interests. But before then, let me introduce myself. I'm a fourth-year assistant professor with a joint appointment in the iSchool and the University of Maryland Institute for Advanced Computer Studies. That means I have two offices, one in Hornbeck and one in A.V. Williams. Because I have two offices, you might want to make sure that I'm where you expect me to be if you come. On Mondays, before class, I'll hold designated office hours. This is my second time teaching the class, and I'm really excited about it. This meshes really well with my research, and I think gives students valuable skills for both research and the job market. I was born in Colorado, and that's where most of my family live, but I grew up in Iowa in a small town called Keokuk, and that's what I consider my hometown. I briefly went to high school in Arkansas and did my undergrad in California at Caltech. I went to grad school in New Jersey, and I had some brief jobs in between working on an electronic dictionary in Berlin and working on the Google Books project in New York. One thing that sometimes causes confusion is my name. So my OIT username is Ying, Y-I-N-G, and that is actually going to me. That's my wife's family name. For research, however, I go by Jordan Boyd Graber. That's what I publish under. The reason why I chose Ying as my username is that I don't particularly like my last name. It's a hyphenated name, it's very hard to spell, it's hard to pronounce correctly. I really don't like it very much. So please, everybody, just call me Jordan. It's what I prefer. I think it leads to a better atmosphere for the class. I also answer to JBG. That's fine by me. Next, I want to talk about the very basics of the technology that we'll be using in this course. And those technologies are R and Rattle. So first, why use R? It's free. Unlike a lot of the other statistical packages out there, it's free both in terms of the cost and in terms of its development. R is developed by a worldwide community of scientists and open source developers, which make it more vibrant and robust than any of the paid packages available. And it's become the standard for statistical data science, both in academia and in industry. It's used by major corporations like Facebook and Google, and if you read any modern scientific paper in statistics, it will use R as its weapon of choice. And this means you can go very deep if you want to, in terms of both the science and the data. In this course, we're going to focus on a subset of the capabilities of R in the package Rattle. And I've chosen to do this because it introduces the vast power of R through a fairly easy GUI. And this allows you to do 90% of what you need without having to go into the arcana of using a command line. The other thing I like about it is that it doesn't hide the command line from you. So if there's something particularly interesting that you need to do that isn't supported by Rattle, you can see what Rattle is doing on the command line and use that as a starting point to get into the more complicated stuff that you need to do on your own. If you can, I'd like you to try to install R before you come to the first class session. Particularly for Mac operating systems, it's very important that you download version 2.14.2. If you download a later version, you will get errors when you try to install Rattle. After you've installed R, you may want to install an integrated development environment for R. For example, using RStudio. I'll put a link to both R and RStudio on the course webpage so you can easily download them. However, all these tools are pretty useless if we don't have data. So where can we find data? Thankfully, data are becoming easier and easier to find. Data.gov is a major government initiative to allow more accountability and transparency to what government does, and allow us to find efficiencies and patterns in what our government does for us. There's also a lot of international data available. There are also organizations like InfoChimps, the Linguistic Data Consortium, NCBI, and Bitly that have collected interesting data sets over the years, particularly in their own subdomains, that are great starting places for research. And then there's also just the wild, wild web. There are many data sets available out there that you can find by Googling around or by crawling the web yourself. Devices like smartphones and Fitbits are also generating lots of data that you can take advantage of. One important source of data is your own research. And I encourage you to think about how you can use the tools that we're using in this course to help you better understand your research goals. And this is part of your first homework assignment, to find some data that you care about and describe it. Let's take a look at a small piece of data that I've put on the web. I have a link here on this slide, and there's also a link on the course webpage under the first lecture. Now, if you download this and open it up in a text application, you'll see a bunch of data fields separated by commas. If you open it up in your favorite spreadsheet, like Excel or OpenOffice, you'll see that these commas separate columns in a data set. This is a bunch of weather data from weather stations in Australia. And so why are the data organized like that? These are called comma-separated value files, and it's a carryover from punch cards, where it was easier to type a special delimiter between fields rather than counting up the number of spaces and putting it in a nice format. And it's a fairly common interchange mechanism because it's basically the lowest common denominator. There are libraries in every programming language you can think of to read these data. You can easily import it into a spreadsheet and edit it there, and just about any application or device will have an option for exporting to comma-separated value data. I'm going to very briefly show off Rattle, how you can install it, start it up, and play around with some of its features. Now, for the moment, I'm only going to be showing off its coolness. I'm not going to explain many of the details. The goal is to get a sense of the data in the spreadsheet and what we can do with it. For example, predicting when it will rain. In the next couple of lectures, we'll talk more about what's actually going on so that you can follow the hows and the whys and the nuts and bolts of what's going on. But for now, the goal is just to do something cool and to make sure that you have a working installation of Rattle on your computer. Once you've downloaded R, you should see a screen that looks like this. The way you interact with R is on the command line, so you need to type in to tell it what to do. The first thing that we need to do is we need to install Rattle. So the command to do that is install packages. Now if you ever have a question about any of these commands, you can just hit question mark and then the command you want more information about, and then the help screen will come up and you can read what you need to do and what all the options are for the command. For now, what we want to do is we want to install Rattle. So we type in the name of the package enclosed in quotes and then hit enter. After it's downloaded the files, we now want to use this library that we've downloaded. The command to do that is library, and then the name of the package. So we type in Rattle, and it is now loaded. So we can use it, as it says here, by typing Rattle. And then open parentheses, close parentheses. We do this because Rattle is a command. It's a function, and all functions need to have some number of arguments, and those arguments are provided inside these parentheses. In this case, Rattle takes no arguments, so it's open parentheses, close parentheses with nothing in there. So we press enter again, and Rattle will start. When you run Rattle, it may ask you to install additional packages. Just say yes to all these questions. Now, as I posted about on Piazza, there's an issue with R version 3 and OS X. So we're using an older version of R that doesn't have these issues. So we're going to be spending a lot of time with Rattle, but today all I wanted to do is to give you a brief example of what you can do with R. So what we're going to do is we're going to load some data in by clicking on the file name folder, and then I've downloaded a file called weather.csv. This is available in the slides. I've added that in. I'm going to hit execute while it loads. And then you see all of the data that have been loaded in. And we'll talk about what all these things mean a little bit later. But for now, you can, as long as it looks like this, it's done what it's supposed to do. We're going to go to the Model tab. We're going to build a tree out of these data and click Execute. So it will present some information, so that's good, nothing went wrong. Our goal right now is just to kick the tires of the car and to make sure that it does the things that it needs to do. So we're not going to talk about the details of what's happening much, but let's click on the Draw button. And this shows you what the model did. And so So the first question it asks is the pressure high or low? Then depending on the answer to that question, it looks at whether it is cloudy or if there's a lot of sunshine. And based on the answers to these questions, it decides whether it will predict that it will rain tomorrow or not. In Homework 0, I'll ask you to do exactly what I did just now. The goal of this is to demonstrate that you have a working R installation on your computer, and so we can work through any problems that you might have before you have to use these programs for real.